Hi, I'm Jeff, and I'm a senior analytic trainer at SAS. In today's video, I'm going to talk about missing value imputation using SAS. The application I'll be using is Model Studio, and it's running on SAS Viya. Now first, what is missing value imputation? Well, you probably know what I mean by missing values. I'm talking about having a data set where there's one or multiple variables where certain observations are missing for those variables. Missing value imputation is the process of simply plugging in some reasonable guess whenever that value is unknown or missing. Now, in business data, there's three reasons we might encounter missing information. One might be due to no match on merge. In business data, we're often merging tables together. Well, if we've got a customer that exists in one data table, but they don't exist in the other data table, when we merge the data together, that customer is going to have missing information on some of the variables. Another reason we might encounter missingness is non-disclosed measurement. Some information like age, income, net wealth, people don't want to self-report that information. So if we're expecting customers to provide that information for us and they don't, again, we're going to have missing values. And another reason we might encounter missingness is due to a non-applicable measurement. Suppose we work for some retailer and our customers can sign up for a VIP program. And one of the variables we have is time since last purchase while being a VIP member. But if somebody has just signed up to the VIP program and hasn't made a purchase yet, we can't measure that variable for that individual. Again, missing information. Now, why do we need to worry about imputing for missingness? One of the big reasons comes down to complete case analysis. Many machine learning algorithms, in fact, traditional regression models, only use the cases that are complete. So if we have an observation or a record and some of the quantities are unknown, then certain algorithms are going to ignore that record when they construct the model. We're essentially reducing the number of observations in the training data because we're only using the ones that are complete. Therefore, we're potentially biasing the sample, and building a model on a biased sample is not a good idea. Another reason comes later down the line. Suppose we've got a final model and we're deploying that model into production. So we're scoring new records in order to make predictions and then use those predictions to make business decisions. But again, if a record comes in to be scored and some of its values are missing, we're not going to be able to make predictions for that particular case. Now, some modeling algorithms actually can deal with missing information. Decision trees and tree-based methods have an ability to deal with missingness. They don't use complete case analysis to construct the model. So therefore, it's not as important to impute when building those types of models compared to some of the others. Now, what are some different ways that we can impute? One simple approach is to simply calculate and then plug in some summary statistic. Let's take the observed values for a variable and calculate the mean, the median, maybe even just take the minimum or the maximum and plug in that one summary statistic whenever we have unknown information. Another approach might be a more distributional method where we take all of the observed values, throw them into a hat, and whenever we come across a missing value, I'll just randomly grab a value out of the hat. Now, I'm not saying that that approach is better or worse than plugging in a summary statistic, but if I do grab values out of a hat, that is giving the chance to plug in different values each time we impute. And yet another way that we might impute is to actually build a model using variables that don't have missing information to predict the variable that is missing. Now, at the time I'm sitting here recording this video, that method is not available yet in Model Studio. But maybe by the time you see the video, it will be available. My contacts in R&D tell me it's on the roadmap and it should be available soon. So before we jump into data, one more comment. Here's a trick that you might want to consider when doing missing value imputation. Using missing value indicators can often give you better predictive models. What I'm talking about here is creating a new variable that is simply indicating whether the original variable was missing or known. It might seem strange, but sometimes just knowledge of missingness, simply knowing whether the original variable was missing or not, can improve the predictive capabilities of the model. All right, let's go ahead and jump into some data. All right, here I am in Model Studio, and I'm on the Data tab. And for this application, we're going to pretend that we work for a grocery store that sells organic products. And we're interested in building a model to predict the likelihood that a customer purchases an organics product in the future. We've got a single target variable. It's actually at the bottom of the table shown here. That's a binary target indicating whether or not there have been organic purchases in the past. Several of our input variables are demographic in nature, and several of the input variables are describing prior purchase habits for the individual customers. Now, right here on the Data tab, I can get my first bit of evidence if we have missingness in the data. Let me scroll a little bit to the right until we see a column labeled missing. The missing column tells us the percent missing for each particular variable. So you'll notice the first variable listed on the table has almost 5% of all of its values missing. There's another variable that has over 11% of its values missing. And just by looking at that column, we can see that most of the input variables have at least some fraction of missingness. So we know it's an issue. As we move forward in the analysis, we should consider imputing for missingness. I've pre-built a couple of pipelines and even pre-run a few of them just to help the video go a little bit quicker. Let's take a look at what I've done. Now, the first pipeline I have called no impute. So in this case, I'm not doing any imputation. I'm going to build a model using complete case analysis. In this pipeline and in all pipelines, I've decided to build a neural network. That's selected more or less arbitrarily, but it is an algorithm that uses complete case analysis. Neural networks have a tendency to overfit the data if we don't select inputs before they're built, so that's why I've got a variable selection node in the pipeline also. Let's take a deeper look at the data just to see a little bit more evidence that we have missingness. I'll take a look at the results of the data exploration node. First of all, let me point out the total number of observations that we have here. You can see in the upper left-hand corner, all the data consists of a little bit more than 22,000 observations. Now, certainly in terms of the size of the data that Model Studio can handle, that's not a very big data set, but I think it's going to be appropriate for this video. Let me scroll down and find a chart that summarizes missing information. Let me maximize the table called missing values. In this plot, on the horizontal axis, we see the variables that contain missingness ranked by the amount or percentage of missing that they have. So demographic gender is the variable that has the highest percentage of missingness. That's the variable that had about 11% missing. In second place comes demographic age with about 7% of its values missing. Let me restore that plot and close the results. So we definitely have missing values. We definitely should be imputing them. Let me take a look at the neural network and see what has happened given that we didn't impute in this case. I'm not really interested in the results yet. Let me just see how many observations were used. And the information that I want is going to be at the bottom of the results in a table called output. Let me maximize that window. It's showing us the output from the underlying procedure running for this model. And the key information that I want to point out is at the top under model information. Look at the number of observations read, a little bit more than 13,000. That's the size of the training data set. But look at the number of observations used, just more than 10,000. So a little bit more than 3,000 observations were not being used to build this neural network because they weren't complete cases. We've reduced the amount of training data, possibly biasing that sample. Not a good idea to have this model built on a biased sample. Let me restore that table and close the results. Let's take a look at a couple of other pipelines. The next pipeline I've built, I've called default impute. Let's see what I've done there. Let me select the imputation node. Well, and as you might guess, I've called this pipeline default impute because I'm just imputing using the default methods. I haven't changed anything in the properties panel. Look under class inputs. Class is just another term for categorical inputs. You see that the method is count. I might also call that modal category because what we're doing for categorical variables is taking the individual category that is most frequently seen in the data, and anytime we encounter a missing value, we're plugging in that same quantity each time, the same category. Under interval inputs, you'll see the method is mean. That just means of all the observed values, we're calculating the mean and plugging that one quantity in. By the way, that mean is actually calculated on the training data, and then we don't recalculate that later on. We use that same value to impute on the validation data, and even later down the line when we're deploying the model, it's typical to use that same quantity again. Now, I want to say one thing about those particular properties. In an earlier video I did on transformations, I showed you how you can establish rules on the data tab and then actually invoke the transformations with the node itself. I could do that same thing here with imputation, but I won't just to save some time. Maybe for some variables I wanted to impute with the mean, but other variables I wanted to impute with the median. I could define those rules on the data tab and then actually invoke them by running an imputation node. Well, let's take a look at the imputation results. And I'll focus on the imputed variables summary table. I'll go ahead and maximize. Now, before I describe the table, just a quick word on how Model Studio handles metadata. The original variables, which were inputs, now have an updated role of rejected. That doesn't mean they're deleted, it just means that they're essentially turned off and would be ignored as we move forward in the analysis. And Model Studio has logically named new variables, and these new variables will be inputs and fair game as we move forward in the analysis. Since we've done imputation, Model Studio has given a prefix of IMP on all the variables that required some imputation to be done. Notice the method column. Some of the variables were imputed with a mean, some of the variables were imputed with a count. Well, that's because some were interval and some were class variables. Now let's look at the value column. We see that for demifluence, the value imputed is 8.7. That's the average value of those values that have been observed on that variable. Everybody that's missing is going to be plugged into that same quantity. Look at demographic cluster, group, one of the class variables. Notice the value there is C. So of all of the categorical values for that variable, C was observed most in the data, and so we're plugging that one quantity in anytime that variable is missing. Let me restore that table and close the results. And again, let's see what the neural network did. Again, we'll look at the performance later. Right now, let's just see how many observations it used. Scrolling down and maximizing the output. And there at the top, now we see something that looks a lot better. Number of observations read, 13,000 and some change. Number of observations used, 13,000 and some change. So now that we have performed imputation, all records are complete, and therefore all of the observations are being used to build this model. I'll restore that table and close the results.
Phew.
Let's look at another way of doing imputation. The next pipeline I've called distribution impute. You can probably guess what I've done here. The imputation node is selected, and take a look at its properties. For class inputs and for interval inputs, I've made a change. Notice that both of those methods are using distribution. So this is the scenario where we're throwing all of the observed values into a hat, randomly grabbing one out, and doing so each time, therefore potentially plugging in different values when we have missingness. Again, let's take a look at the results of imputation. and I'll maximize imputed variable summary. Same scenario in this pipeline. We've got new variables that have been created with an IMPP prefix, and all of those variables now have a role of input. Notice the method column. All variables are being imputed with a distributional approach. Notice the value column. For each variable, it says varies because we're grabbing different values out of that hat of observed values every time we're imputing. That means we're going to get different values when we impute. Let me restore that plot, close the results, and now we'll look at the final pipeline, which I will need to run. This final pipeline I've called indicators and default impute. Let me show you what I've done in the imputation node here. Now, in terms of the imputation methods, I've stayed with the defaults, count for class inputs, and mean for interval inputs. But here I've created those missing value indicators. Look a little bit further down in the properties panel under indicators. I've asked for unique indicators to be created. That means for each individual variable where there's missingness, a corresponding indicator variable will be created. And also notice the role that I've assigned for these indicator variables, input. That means these missing value indicators are going to be fair game as we move forward in the analysis. They're input variables just like everything else. Now, let me go ahead and run the pipeline. And while it's running, I'm going to tell you that I'm going to do a few different things when we look at the results here. For the imputation node, I'm not going to go to the same table we saw before. We should be pretty comfortable with it now. I'm going to actually show you the output data table itself. That's kind of like looking at the data after the imputation node has done its job, and I want to show you what it's passing on to the next node. Particularly, I want to show you those missing value indicators. I'm also going to show you the results for the first time of the variable selection node. We have these missing value indicators created. It's certainly not a guarantee that they're going to be selected, but if they're predictive, they might be selected by that node and passed on to the neural network. So we'll do those things in just a moment when the pipeline's done running. All right, results look ready. Let me start with the imputation node. We'll look at results. And again, what I want to do is look at the output data. So I'll select the output data tab and click view output data. I'm not going to sample the data, so I'll just click view output data again. All right, the table is ready, and it looks like we've got to go pretty far down a column, but if we look at a fluence grade, oh, I don't even know. Maybe by the time we get down to about 20 or so observations down the list, we've got 2 observations back to back that are missing for that variable. Let's scroll to the right and take a look at the imputation for that variable and also the missing value indicator. All right, that's far enough to see the imputed form of that variable. Now remember, the original demographic affluence variable is going to have a role of rejected. The imputed form of that variable, which should be this column right here, now has a role of input. The first 20 or so observations maintain the observed value seen before, and then down towards the bottom of the list is that value 8.7 that we saw earlier plugged in. That's the mean of the observed values. Let's take a look at the missing value indicator for that variable. And here it is. Let me make the header a little bit larger for you. Missing indicator for demofluence. This indicator is indicating missingness. So if the original observation was known, the indicator is 0. If the original information was missing, the indicator is 1. Notice as we look down the column, we've got a bunch of zeros. Then towards the bottom, we see the 2 missing cases we had before indicated back to back with 1s. The missing value indicator is going to be input and passed forward in the analysis. Let me close those results. And let's take a look at the results of variable selection. Did we pick up any of those indicators? And I'll start by looking at the variable selection table. The variable selection table tells me whether variables were selected by this node and therefore passed on as inputs, or whether they were ultimately rejected by this node. Any variable on this table that has a blank in the reason column has been selected and is input going forward. We've got a handful of them at the top, and notice the bottom one there, m_dem gender. Well, the M prefix stands for missing value indicator. So the variable selection node believes that that missing indicator is predictive, it's been selected, and it's going to be passed on to the neural network. Let me restore that table and close the results. Well, let's take a look at the final punchline. Let's take a look at our pipeline comparison. Let's compare each of the models from all of the pipelines. Now, to be fair, the neural network that was built on complete case analysis, that's the one from the pipeline called NoImpute, it's not really fair to compare that model with the others because it's technically been built on a different sample. It's okay to compare models, even models of different algorithms, as long as they're built on the same sample of data. Here, the NoImpute neural network has been built on a subset of the data that the others were built on. But nonetheless, we've got it here in the comparison, and it might just be useful or interesting to take a look at it. Well, what model is best? I'm using average squared error here to pick the champion model. And I hate to say I told you so, but in this case, I told you so. The neural network that used the indicators and the default impute is best based on average squared error. Now, I can't guarantee those results all the time. In data science, results are always data dependent. Missing value indicators might not always help, but in this case for our organics data set, they sure did. The model that came in second place was the neural network that didn't use indicators, but did the default impute. And then the neural network that came in third place is the one where we did the distributional impute. And there in last place, again, might not be the fairest of comparisons, but the neural network built on complete case analysis, built on a subset of the data, is in last place with the largest average squared error. So that's it for this video. Please take a look down below for additional resources. Also, feel free to leave me a comment or ask me a question if you've got one. Don't forget to subscribe to the channel, and if you like the video, give me a thumbs up. I hope you learned something along the way. I hope you had a little bit of fun. That's it for me. Until next time, I'll see you later.